this is what image quality assessment tries to tackle. How do you automatically, with an algorithm, receive an image and assess if it's good or not? Because the quality of the images are very important for following processes, like deep learning, when you use convolutional neural networks. If you receive, if the model is not expecting bad quality image, then it's not going to work properly. Or compressing. If you want to compress an image, you want the human not to notice that it's compressed, but you want it as light as possible. These kind of things are why these kind of models exist. So I'm going to show you, this is how I split the presentation. First, an introduction to this, a literature review, some of the models, architectures, the performance of the models and architectures, a code example, an application, and conclusions and Q&A. So just for you to know me, I am a data scientist and I work for Property Finder. I've been here for a year and 2 or 3 months working on several stuff. One of the applications is this, but I also work with text and other kind of data like time series on this kind of stuff. So as I said, what is image quality assessment? So the fancy definition is quantitatively represent the human perception of quality in images. That's good. I just described it with the image before, but this is like a definition. And why is it important? Because these metrics can be used to measure the impact of quality into several other kind of algorithms like compression, image transmission, or image processing. There are several types of distortions, and you can find this in several areas in image process. For example, this one is very common, compression. Websites want their sites to be as fast, to load as fast as possible, you know? But you don't want to compromise the quality of your product. So you need to figure out, you need to optimize the image compression so you can show the best content and have the images as light as possible. You can also have additive noise. This happens commonly with image transmission. When you move an image from one side to other side, it can lose some quality. This can happen. Also, this happens when the camera, for example, the phone camera at night, to take a picture, if the lighting conditions are not good enough, you can have some additive noise. So this happens. If it's daylight, it's fine. But at night, this can happen. Gaussian blur. If you don't focus correctly your camera, sometimes this is on purpose for art sake. But normally we don't want it. And this is one of the most difficult ones. Hard to, because as you can see, this one you can identify it because it's kind of clear, and for computers it's easy to identify. This one too, because there's something called pixel structure, and we expect the structure to behave in a way, and I'm going to show you later. And the original one, the nice one. So a little bit of theory behind this. There is a lot of theory behind, but I'm going to try to simplify as much as possible. And please stop me if I'm going too deep into the technicalities. But basically, we have 2 different types of algorithms for image quality. Full reference and no reference. Again, what do you think is full reference? A full reference will be, I have it later. A full reference will be, I have the good quality one and the bad quality one. The good quality, the bad quality is called distorted. And so I have the good quality and the distorted. And then I input these 2 images into something, and I get a number. Let's say between 0 and 100, 0 is bad quality, 100 is good quality. But this, in real applications, do you think we have the good quality image? I don't think so. It's very uncommon to have the good quality image. We cannot compare in the real life how does the image should look like. So that's why we also have no reference. You have the bad quality image, and you input it into a box, and the box automatically, without any more reference, gives you the number. This is the most common, or in literature they are focusing more in this kind of algorithms, because it's easier just to have the image, input it into a box, and get the score. So this is like a drawing of the several paths that image quality assessment can have. But let's focus on the terms of today. So we have full reference and blind. Blind means no reference. And full reference, you can have several algorithms like SSIM and all these acronyms. I don't remember what they mean. The problem with this is you need the good quality image. And then you have the blind ones. And the blind ones split into two, the old ones and the new ones. The old ones need for you to input which kind of distortion does the image have. That doesn't make sense. If I already know what distortion it has, then I don't need the algorithm. And you have the general purpose, which means I don't have any context about the image, and I want to know how's the quality, good or bad. So let's talk about those ones. For those ones, we have another two paths. Handcrafted features and learned features. Handcrafted is someone very smart just figured out that the images behave in a way, and this is how you can describe the quality. So the human created some algorithms and then transferred the knowledge to some box. And feature learning is, I take the image and I learn how is bad quality and how is good quality. No intervention at all. So the handcrafted features are easier to program because they are kind of, I'm gonna risk here the definition, but deterministic, in a way that you don't need a lot of complex knowledge to use it or to train it. So one of the theory behind all of this is natural Bayesian statistics. So the theory says all the images that you can take outside the world with your camera behave as a Gaussian distribution, generalized Gaussian distribution. So we start from here, and then the pictures that are not behaving like a generalized Gaussian distribution are bad quality. The ones that does are good quality. That's it. And then we have the feature learning. So basically, this one takes a lot of examples, and tries to figure out what are the vectors that represent the quality of the image automatically. So basically is, I take the image, I train a convolutional neural network or unsupervised code book based, and then I get the quality. So I extract the characteristics of bad quality and good quality, and I represent it in a vector. So first, the easy one, RISC. It's an algorithm that was created, I think, 2012. And the theory behind is, as I said, natural Bayesian statistics behave this way, and everything that doesn't behave this way is bad quality. Easy. And the concept is very easy, as you can see. We have a normalization of the image, and that's it. You have this. And this is the main statistic, and these statistics are calculated based on this one. So it's easy. How can we calculate the features? So we take these distributions and we try to figure out the parameters that get the best fit of the generalized Gaussian distribution. And those are the features to use. You take these features, you put them into a regressor like SDM, some tree, a boosting or something like this, and then you map it to the subjective score. How is this created? So the main problem with the training images is it's very expensive and hard to get images tagged with the subjective score. Because the methodology is, for example, we have this group, and I will take an image and another image, and I will say, for you, this is good quality or bad quality, and if it's good quality, from 1 to 5, if it's bad quality, from 1 to 5, how bad it is. And you ask several persons, and then you take the distribution. Very expensive. And then you have more complex methodology, like DIQA, Deep Image Quality Assessment. I remember. So this seems complex, but it's not. You train all of this, and then you train this small part. This one needs a lot of information. This one doesn't need a lot. Generalize it better. The performance. So you have. I didn't cover the other ones. If you are interested about the other methodologies, you can contact me and I can share. But basically, we covered these two: handcrafted and learned. And as you can see, these are the most common data sets out there to test image quality assessment. So the super complex against the simple one. And the differences are not quite big. So this means that if you need like a very, very specific performance, you should go for this. But we want to make money. So we go with the easy one, no? And then we iterate. That's it. Just for knowledge, these numbers are not accuracy. These numbers are correlation between subjective score, the human ones, against what the algorithm got. So 1 is perfect correlation, 0 is no correlation. So they basically do very well, above 85 correlation, not 85. A little bit of code. I'm going to explain the easy one. So basically you have this is the formula that explains everything. And it's comprised of 3 elements: the image, the mean of the image, and the standard deviation of the image. This is just, what happens if this is 0? Bad things happen, no? And we don't like bad things. So this constant is included, so you don't have 0. Even if this is 0, you will have something here. And then you have a Gaussian kernel, which is the mean. This is just saying this is the weight of a Gaussian kernel, and this is the image. So this is just a convolution. And then you have the local deviation, which is another, oops, I pasted wrongly. I will fix this. By the way, this presentation is already online. I'm gonna share with you the link after I finish, so don't worry, you don't have to take pictures. Everything is open source. And there's an article too. So this is wrong, but this is right. So as you can see, it's a convolution. And the only thing that changes is the image is just the square of the original. That's it. So easy. Two convolutions and the original image. This is the tricky part. How do I find the parameters of the Gaussian distributions? This way. You can see it later, and you can also ask me, because I don't remember what I did. Okay, the equation I showed you before, this is called mean subtracted constant normalized coefficients, MSCN, for simplification. So the MSCN behaves this way, which is much simpler because we assume it's symmetric and simplifies a lot. But the other things I showed you are not symmetric, which are the ones that, let me see here. These other 3 to 18, like 15 features, are generated from pairwise products from these coefficients. These ones, sadly, do not behave as a symmetric Gaussian. So you need to calculate an asymmetric generalized Gaussian distribution. And it looks like this. Quite ugly, I know. So basically it says that behaves like a normal thing, but the variance in the left and the variance in the right are different. That's the only thing it's saying. And then, for example, for feature 1 and 2, you fit all the MSCN to the Gaussian, you take the scale, the shape, and the variance, and this is feature 1 and feature 2. And then you fit the rest, the pairwise, you take this, you take this, and another parameter is not here, and these are other features for the other 4 pairwise products. Just some multiplication of this one. That's it, 2 shifts. And you have 18 features in the end. So it's not very complex. You train a model with 18 features, it's okay. And this is the easy part. So you take the other things I showed you, you normalize, because it's good to normalize before you train a model, and you train a support vector regressor. Support vector machine regressor. And that's it. Why this and not a convolutional neural network? As I said, the amount of samples we have is small, and the amount of samples you need for a convolutional neural network is very big. So you use something that generalizes better with a smaller size of the data set. So the application. The theory is good, training stuff is very interesting, but we have to make money. If we don't make money, then nobody is going to be interested in this. So let's make some money. At Property Finder, we have a very big issue. We rely on the images that the agents and the brokers send us. If the images are not good, it's okay, because the current quality score just counts the number of images, and that's it. Easy. So the agents do it because they want to sell. So the more expensive the property, it's more common to have better pictures. But what happens with the rest, which is the 80% of the listings? They don't care about the quality. They just take some images and upload them. And as we don't penalize this, they have fun. But we don't have them to have fun. So, these are some examples that we don't like to have. So, portrait and bad lighting conditions. This one we don't like. Because what is this? You have a door and some light outside, and the rest we don't know. This one is a good one, no? I can even see the patterns in the floor and the wood and everything. This is good. This is what we have, what we want. We have this. Okay, it's the entrance of something. I don't see the floor. I see there's a sofa, but what is the cell phone made of? I don't know. So is this synthetic? Is this real? I don't know. So this is bad quality. And this, everything's red. And the rest, I don't know. Which one you would rent, by the way? Right. Yeah, me too. So we applied this algorithm to all the listings and images in our site, and we got this distribution. 100 is good quality, 0 is bad quality. So as you can see, the dispersion here is big. So we can have terrible pictures, and they are distributed across the horrible threshold that you can see here. And then there is a lot of very good quality, but it's concentrated here. So the bad are very bad, and the good ones are consistently good. This is what it means. And as you can see, it's not very bad. I mean, the quality goes from 70 to 90 or something like this. So but this is for the UAE. I'm not showing the things for Morocco or other kind of markets that are emerging. It's not gonna be like this. It's more, it's slower, believe me. I've seen horrible things. I've been honest. I don't know what people have with bathrooms, but it's always the first picture. Like, well, the first picture is a bathroom. Okay, for me it's important, but it's not the first picture I want to see. I want to see the sea or the garden at least. So this is the evolution of the quality score over time. I can talk about that. We have like 10 minutes still. So,
one more question.
You have another question? Okay. Later I talk about the deployment of this monster.
Hi. Did you try to also incorporate website analytics with your image recognition or like image quality? So, for example, when trying to connect, of course, it's trivial to know that if you have good quality images, you will be able to sell or rent a property. But did you also manage to calculate the time spent on the listing, the amount of time the listing was on the website, or like, did you incorporate any of the website analytics into your evaluation of the listing, or just the image?
These are the kind of questions I have to ask my boss if I can answer. The answer is yes. We did. That's how we measure the impact of the images through the statistics you mentioned.
But I can tell you, so the guys are not disappointed, I can tell you that from my experience at the Visible, the better quality of images you have, more leads, listings get, more visits, it sells faster, and so on and so forth. So it's correlated, strongly correlated. So.
Strongly. I talk too much.
So you said that your model was able to describe what's bad in the image. So how did you know that this is the lighting condition, if this image is bad, or the resolution is bad? How did you exactly know from your model?
You got the trick. All right. I said that we can explain different areas of quality, but I am just mentioning the noise part. We have resolution, we have lighting conditions. These are the things I really can't talk about, but I will tell you one thing. It's another model, completely another model. So basically for each of the pillars, as we define the score, each pillar contains a different model. And each pillar describes the image in a different way, in a different area. So yes, there's another part I didn't show. It's part of the secret sauce. We don't show everything.
Very quickly, everyone when talks about image recognitions and creation, the style of applying or start looking at using GAN models? Have you considered it as an area you're going to look at?
These are very interesting ones. They are used to tackle the problem with lack of data. So you're trying to generate synthetic data that is kind of realistic. And the answer is no, because what we are trying to do is also quite tied to the business side point of view. So we're trying to get the core or the basics for all the applications, in this case is image quality, and then we can iterate with more things. So in the path, I think in the path, it's better to include DIQA, because we don't need to generate a synthetic model, which is GAN. We can use 2 stages. The first one is to learn the features, automatically learn the features from a huge, like ImageNet, huge database, and then you train the small model to the subjective score. So basically, the problem is not the lack of data, but it's more about the lack of subjective scores associated to the data. So that's why we haven't gone that way, but it's a very interesting area to explore. It's how GANs are adversarial networks, no?
Yeah, generative adversarial.
Generative adversarial networks. Thank you.
My question is, I find the topic very interesting.
Thank you.
If I want to start learning about image quality, for me, image is about, it has to learn fast from e-commerce point of view. That's my experience. Where can I start if I want to see image from a different perspective? Like from your angle, where image is very important to everything. That's
Images are very important, yes. They sell stuff.
I want to start learning.
Yeah. So the question is, where can you start to learn these kind of things? Or where can you start to...
As interest to learn
In general.
Statistics.
Huh?
You should start learning statistics. Okay, then signal processing next.
Oh man. Okay. This is so image processing is or computer vision. So if we go to the wider, which is computer vision, then you go to the deeper, which is deep neural networks and this kind of fancy stuff. Image processing is a field that is enormous. It's huge. So to really understand what's going on with all of these things, you need to learn the basics. So you can go from, I mentioned something called the human vision system, which is anatomically how the eyes work and how the information is sent to the brain. And all of these kind of algorithms come from there. So maybe it would be good to start from there. It's a very good advice. When I started to do all of this stuff, I started with the neuroscience, how the brain works. This is the best way to learn, because currently people is trying to learn, like they go straight to the deep learning, and it's like, yeah, you have nodes and you have coefficients and it works, okay. But if you don't understand where it comes from, then you are missing a lot of information. So from there, you have to learn about images. Something I did was I got a girlfriend, that that was a photographer. So you learn a lot of stuff. Maybe you can find a girlfriend that is a photographer. And you can and she will explain you about how images can be represented as histograms of pixels, and how these histograms are for different channels, and how you can modify the histograms to give contrast or to give lighting or all these basics. So human visual system and my girlfriend photographer.
I have one. Is there any work being done locally on digital pathology?
Again, sorry?
Pathology, the images of the pathology,
Like-
lab
like-
images, yeah.
Like these diseases or something like this, or pathology in which way?
You just spoke about histograms, getting histograms from the images. So like counting cells, blood cells.
Yes.
Is it done locally, anything out here?
In this area?
Yeah.
Whew. Not that I know, but
There are some companies in Abu Dhabi that work in this.
that's what I was going to say, but those companies are related to the government, so it's kind of close.
So
You can talk to the government, they know. Is someone from the government here? No.
There's always someone. There's always someone from the government.
I just need to ask, how would you compare risk with something like NIQE or
DIQA?
NIQE?
NIQE.
Yeah,
NIQE. You got me there. What's that?
like it's like slightly different.
Technique.
Yeah.
So basically what you do is it's very basic actually. Scientists are very smart, but they like to compete in a very strange way. So the correct way to do it is to statistically compare the results. Basically, you do this cross validation and you create the accuracy and all of this, but they don't do it. No, it's not fun enough.
No, but it's here, I guess, this
Yeah.
NIQE.
No.
Is-
But the question is how you compare them, and the scientists just calculate the number, and they say, yeah, this is 0.001 better, mine is better. That's it. This is how they do it. But basically, you should create a ANOVA or something like this to compare the significant differences. This is the best way to do it.
So
And compare how much it takes to run one or another.
Oh, this is actually why we picked this. Well, scientists, they don't care about that. We do care because we make money. So I'm going to repeat money instead of machine learning here because it's more important. We picked actually brisk because it runs in like 0.2 seconds, super fast. And the other one is going to take longer. And for this one, so the good thing about this one, because it's not that bad, you can split or parallelize the process with GPUs, which is expensive. And this one you can do it with your local machine, 0.2 seconds. This is also something important to take into account when picking an algorithm. How fast it runs, how easy it is to deploy, the efforts you need to train, and all of this. Good question, thank you very much.
Can you give a brief overview, like let's say you have thousands of images, like what is the technology stack you are using and what Python libraries are already there which you can reuse and
So basically, she's a gardener, that's why she come. I know. Okay. Thank you for coming. Yeah, I can talk about this. Basically, so as you know, and I think it's related to your question, we picked this one because it's fast and it's easy to train and deploy. It's 2018, we can do that. And other kind of things. So I like to give a lot of time for questions, that's why it was kind of short. So the conclusions. You don't always have to go to the shiny thing. You can have very good results with less efforts, and you can later iterate after you justify the efforts. Business rule. And it was very important to split the score into several components so we can give a feedback to the agents so they can improve. We need them to improve because if they improve, our site is better. This is something we would like to have. So this was everything I got. I have a lot of more information, papers and all of this boring stuff, and code that I'm glad to share. So this is my LinkedIn. You can send me a message. These are the slides, so you can have everything. And this is one of the series of articles I'm writing about image quality assessment. You can write about risk. Another one is coming from Property Finder, which is the part of how it's impacting business. And another one is coming about the novel methodologies of image quality assessment. So please, you can contact me and I can share everything. Thank you for the space and thank you for your attention.
Thank you, Ricardo. And then questions? Do you have any questions?
Please don't be tough. I'm shy.
Hi. So you picked 18 features for the model training. How did you pick them? Did you use like a certain feature selection algorithm?
So basically, it's for the risk. This is quite important because this is about 90% of the methodology. So it's 18 features, and it's just you train. Second. So the formulas I showed behave like this. And you can see this as I'm gonna take your task and I will answer you and you can call me later to see the progress of this task. And this is the summary of how it works. So it's an asynchronous pattern. So basically if you move to a more complex model, still the client won't notice it because he's still waiting. He's just sent a request and waits for the result. Transparent and fault tolerant, which is important, resilient. Thank you.
Okay, any more questions?
We still have 5 minutes or so, or less, or maybe no more time.
Okay, if there are no questions, then thank you, Ricardo, for presenting.